dear colleagues, hello everyone. Welcome to our every week microwave seminar. And today our speaker is Thomas O'Reilly. So he'll be talking about the DIY MRI. So about the MRI. So I think he'll tell you about this more than I can do. And so Tommy, please, you can start.
Sure, thanks. Share my screen. Right, so as Dimitri said, I'm going to talk about building your own MRI scanner. So it'll be, I think Elena was asking mainly from the practical side, just to show some of the challenges, but then also just generally speaking, a little bit of an overview at the beginning of why you would want to do MRI, low field MRI, and obviously it's much more fun if you can build it yourself as well. So at the moment, there are three kind of main imaging techniques that are commonly used in the clinic, and they have quite a difference in price. So the ultrasound is obviously the cheapest technique. It's typically, you can buy an ultrasound device for 1,000 or 2,000 euros. But the contrast and the signal to noise ratio that you can get is not great. And you have CT, which can give incredibly high resolution images. And for bones and hard tissue, it's a very good technique, but it has its drawbacks. It's a little bit, or it's quite a lot more expensive than ultrasound, but nowhere near an MRI system. But it suffers from two things. One, very poor tissue contrast, a soft tissue contrast. So if you want to see the difference between gray and white matter in your brain, for instance, CT is not the way to do it. But also, obviously, it's an X-ray based technique, so you're going to have safety issues there. And then you have MRI, which nowadays gives very good resolution images, not as high as CT, but is very strong in image contrast. But the price of these systems is incredibly high. So typically the 1.5 and the 3 Tesla machines that are clinically used nowadays will run you more than €1 million to install at the very least. The 3 Tesla ones will typically be twice the price as the 1.5 Tesla ones. And what does that mean in practice? Well, it means that a lot of the world does not have access to MRI scanners just because it's simply too expensive. It's a very incomplete map, but this was a survey done by the WHO, which shows that in Africa, there is countries which literally have no MRI scanners in the entire country. The project that we're doing is quite closely collaborated with Uganda, and it's a country with a population of more than 40 million, and they have about 3 MRI scanners in the entire country. And those are not the latest generation ones. So it really is a very restricted technology. So what can you do about it? How do we increase the accessibility to MRI? Well, obviously, you're going to have to reduce the cost of the system, but you also have to increase the physical access. And these are 2 points that we feel in our group. We're a little bit biased, obviously, because we like low field, but where low field MRI can probably be quite useful, because to reduce the cost, you have to lower the high purchasing costs, which means you have to use lower cost materials, which typically will mean that your superconducting wires are out, because you need the wires themselves are very expensive, but also the cryostat is incredibly expensive. You have high sighting costs. So the MRI scanner has to be placed in a special room, which is shielded from RF and sometimes also magnetically shielded. So that's very expensive. So you have to come up with a way to reduce the footprint of your system. And then you have your high maintenance costs as well. So your scanner will break, and how do you fix it? Well, for us, that means we have a service contract with Philips, which I'm not sure I'm allowed to share the numbers, but it's more than a couple of euros a day. So it's really very expensive. So can you open source the designs of your electronics so that people can maintain the systems themselves? Obviously, vendors aren't interested in that, but we're not vendors, we're an academic institute, so we can ask these questions. And for increasing physical access, it really comes down to increasing portability, and that's where Hyperfine have shown the usefulness of this. So this is a portable MRI scanner that's been developed by Hyperfine in the US, that you can literally roll to the bedside. So you no longer have the scanner restricted to one room in the hospital. It still weighs a lot, so it's not something you can just take on the bus with you. But at least it's starting to address these issues about portability. So That's a general introduction of why maybe low field is interested. And then now I'll talk about the system design, and I've kind of split it into 3 different parts, going with the name of MRI. So we start off with the magnetic part, which we use to align the spins in the system. So the hydrogen spins. It's a very brief overview of MRI. So I hope some of you have done are familiar with the technique. So we use the magnet to align the spins. Then we use the RF, the resonance part, to excite those spins, and we get a signal out of it. And then we use the imaging system to actually encode the image, so encode the signals that we get out, so that we're able to produce ultimately a 3-dimensional image. So these are the 3 main subsystems of the talk, and that's kind of how I split them up as well going forward. So start off with the magnet. So there's 3, generally speaking, there's kind of 3 categories again that these fall into. So you have the supercon systems, the resistive systems, and the permanent magnet systems. And the superconducting systems are typically made by, well, always made by specialist companies who have a lot of experience in this, purely because it's a very complex thing to do, working with the superconducting wires and also making sure that all the forces are properly balanced and things like that. It's very hard. But these vendors are able to produce magnets. I think currently the highest field system, whole body system, is an 11.4 Tesla system that they've just opened up in Paris. So that's really impressive, and they're capable of achieving very high homogeneity. So when I say high homogeneity of the magnetic field, it's about 1 part per million variance over a 40 centimeter sphere. So that's really not very much at all, but they're incredibly expensive. So the typical number that people throw around is about €1 million per Tesla. So even the lower end of the commercial systems, which are 1.5 Tesla nowadays, will cost you more than €1 million for the magnet alone. Then you have the resistive systems. This is a nice one from Matt Rosen's group, running at 6.5 milliTesla. So that's 3 orders of magnitude lower than the superconducting systems, and that's just because you can't push through too much current through the wires, because you get I2R heating. So typically these are very low field, but they have the same benefit of the superconducting systems, that you can wind that wire in any way that you want. So as long as your manufacturing tolerances are decent, it's quite easy to get a high homogeneity. And then the cost is very low, because instead of you don't need a cryostat, you don't need the nip coat wires and the other superconducting materials. You just need copper and a powerful power supply to run it. And then finally, you have the permanent magnets. So permanent magnets will typically have higher field strength than you can get with resistive magnets, especially nowadays where you have the very cheap neodymium ion boron magnets. But they will suffer from lower homogeneities. I'll come back to some of that later, but basically the magnets that you buy are not perfect in their magnetization, but also it's much less flexible, because you can't just shape that magnet, or you can, but it's very expensive to shape the magnet into any shape that you want. If you use off-the-shelf components, then the cost of a permanent magnet system is probably actually lower than it is for a resistive magnet, because you don't need the electronics. And then the permanent magnet systems, you can then subdivide again into 3 different parts. It's kind of 2.5 different parts, because the yokeless magnets and the homogeneous magnets, there's a lot of overlap there. But I just wanted to separate them because they conceptually work different in MRI. So the way that they generate the magnetic field is the same, but it's just the application is conceptually different. So for the yoke magnets, they typically have some magnetic material at the bottom and at the top. And then you use an iron yoke to basically guide the flux lines coming from the pole pieces back down to the other side. And that creates a very homogeneous magnetic field. The drawback there is that you have to use this iron yoke, and that iron is incredibly heavy. So you typically see that these systems will be a little bit higher in field strength than the yokeless magnets, with the drawback that the weight is huge. So the hyperfine system, for instance, it's portable, but it does weigh 400 or 500 kilos. I can't remember the exact number. And that's because they use this yoked magnet design. It's also very easy to build because it really comes down to one plate of magnet, and then 4 plates of iron. Obviously, the tolerances are a little bit tight, but it's quite a simple thing to construct. The yokeless magnets are typically come in the form of Hallback arrays. You don't see these built as often as the yoke designs, just because they're a little bit harder to build and they have slightly lower magnetic field strength, but they're much lighter in weight. So this is the one from our group, which weighs about 75 kilos. It's a hole for imaging the entire human head. So it's very comparable in field distribution to this, but we're at 75 kilos versus several hundred kilos. But these are hard to build, and I'll come back to that later. And then you have the inhomogeneous magnets, which allows you to be very flexible in design. So they're inhomogeneous, which means that they'll typically have the readout gradient that we use in MRI, the frequency encoding gradient, built into the system. Because you don't need a homogeneous magnet, you can be much more flexible in the design of your system, because, for instance, you only need magnets on one side. It does mean that you're much less flexible in imaging. So you're more flexible in design, but less flexible in applications. The rest of the talk, I'm going to just focus on the yokeless magnet, just because that's what we have the most experience with. So for those who don't know, a Hallback array is one of the yokeless magnet designs. It basically uses a whole array of magnets to produce the magnetic field, to produce a homogeneous magnetic field inside of the cylinder. So to do that, you have your individual magnets with the arrows indicating the magnetization, and that magnetization rotates twice over the circumference of the Hallback array. And that, in theory, for an infinitely long Hallback array with identical magnets, gives you a perfectly homogeneous field that is oriented across the bore of your magnet. So that's important to remember, because typical MRI scanners will use a solenoid-based approach to making the magnetic field, which means that the magnetic field is pointing down the bore of the magnet. But obviously, we can't make infinitely long Hallback arrays. So what we find is that the homogeneity is actually significantly reduced when you reduce that length of the system. So it's 2 reasons, or it has 2 consequences. Your field will drop off along the length of the bore. So this is just a plot of the field basically along this axis here. So you get a very strong, these are a drop off, but you also in plane, you get this, you get quite a high inhomogeneity with this very characteristic ellipsoidal isocontour. So you need to optimize your magnet in order to prevent that field from dropping off. And the way that we decided to do this was by allowing the ring diameters of your magnet to vary along the length of the system. So smaller ring diameters associated with a higher magnetic field strength. And if you place those on the edges of your magnet, so where you're seeing that magnetic field lines drop off, you're able to elevate those to increase the magnetic field there, and that's preventing the field from dropping off. In that way, you really get a much more homogeneous system. And this is one of the practical choices that we made, is that prior groups and other people will tell you to use bigger magnets because you get more magnetic field, which is true. The magnetic field produced by a single magnet will scale with the volume of that magnet. But they become dangerous to work with. The bigger they are, the higher the forces also. So if your finger gets stuck in between 2 magnets, for instance, it can do serious damage. We found that the 12mm magnets, we were kind of a comfortable place. They're very strong. If you let them fly towards each other and you put your finger in between, it does still hurt, but it's not going to injure you. So we like that, but then also using so many magnets, because in the end, so I'll show on the next slide, we used about 3,000 magnets. All the little fluctuations between the magnets themselves, because they'll all have slightly different strength and slightly different orientations and things like that, will be averaged out a little bit by the fact that you're using a lot of magnets rather than a few. And then obviously you want the highest B0 field strength you can get, so we just added 2 layers of magnets onto that. So this is the design that we came up with. It's you really see that effect where you have your smaller ring diameters towards the edges and your bigger ring diameters in the middle to prevent that field from dropping off. And this used about 3,000 magnets in total. And it's supposed to have a homogeneity of 440 parts per million over 20 centimeters, which is really pushing it for whole head imaging, but good enough-ish. Definitely, if you can get that bigger, that 20 centimeter, it's definitely better. So to construct it, we use plexiglass. We use plexiglass because we like working with it, but also the magnets will be in there, and they will be in there constantly, and they will not necessarily want to be in there. So there's quite a lot of force holding those magnets together. So when you're choosing the materials that you're going to work with, one of the things to think about is creep, which basically any typically plastics, if you expose them long-term to forces, they're going to very slowly deform over time. And it's one of the material properties, and you can choose your materials. Typically, the harder the material is, the less likely that's going to happen. And plexiglass is a very hard material, so we felt relatively comfortable using it. And finally, it's also very easy to work with. So we laser cut the plexiglass in our own workshop. Yeah, definitely. If you start going bigger with your magnets, then maybe plexiglass is no longer the correct choice. Maybe you want to go to FR4 or G10 or one of those carbon fiber like materials. But it gets more expensive and more difficult to machine. So choose your materials well here. So this is the magnet that we designed, and if you assume that I work for free, then the system costs about 4,000 euros just in parts alone. And took us 3 weeks to build on my own, but that was an ISMRM crunch period, so that was about 100 hours a week for 3 weeks. So it's we're getting better at building these now, so we can probably build this in about 100 hours now to put together. So that's really not the limiting factor. You will have sore fingers afterwards though, because 3,000 magnets being pushed into holders is not per se fun.
Excuse me, Tom, there is a question in the chat.
Oh.
The question is, did you choose some specific magnets according to their field temperature dependence?
We did not. No, it's a very good question, because there is quite a large field temperature dependence of the magnets. It's about 0.12% per degree temperature change, which if you translate it to frequency for our system, it's about 2 kilohertz. Which we do notice when we're imaging. We can see the system heating up. The reason we didn't choose for it is 2-part field strength. So if you want the strongest magnets you can get, you will come out on neodymium iron boron magnets, and they will have quite a strong temperature dependence. The following choice is Simco, I think, samarium cobalt. Which is about has about a quarter of the temperature dependence, but it's also 10, 20, 30% weaker. So it's kind of a trade-off that we made. Patient first, gradient system second, RF not. I don't. Pretty sure it's not RF. The question was does the temperature change? Yeah. There's other materials that you can choose, which actually have there's a very cool paper which balances you have materials with a negative temperature gradient also, which get stronger the hotter they get, and you can balance them out so that you have a temperature insensitive magnet. It's very cool work, but what you're always doing is you're compromising the magnetic field strength. So we kind of made the choice, like, we know there's going to be some variation there, but we can deal with it in post-processing and during the acquisition itself. And then we'll have more signal to work with because we'll have a stronger magnet. So to map the magnetic field, which is also very important, we built a 3D positioning robot, which is based on the COSY measure. Shared, it's an open source design shared by Lucas Winter from Berlin. And it's essentially a glorified 3D printer with an arm stuck on it instead of a print head. And yeah, it's cool to build, and it's definitely one of those useful things that you should have in your lab if you're going to build your own magnets, just because the amount of time it saves having accurate B0 maps to work with. So these are the maps that we then acquired from that system, and you can see that, well, generally speaking, if you ignore the color scaling a little bit, there's quite good agreement between the two, except for one thing, which is that the homogeneity is way worse than what we simulated. And it took us a while to understand this. So you always be prepared to shim your system. Like, you build your magnet, no matter how well you build it, it's always going to be worse than you simulate. We just didn't expect it to be this much worse. And it took us a while to understand where that was coming from. So this is the first system that we built here, and these are the three views. So this is a front view, this is a top view, and this is a side view of the magnetic field. So this is all in the center of the magnet. And what you see is this z squared, because z is our main magnetic field direction, so it's across the board. It's a z squared minus y squared field dependence. So we have a quadratic increase minus a quadratic decrease in this direction. And if we look at some of the other magnets that we've built since then, we see the exact same field pattern. So this is a 87 millitesla wrist magnet that we constructed. And again, the homogeneity for all of these is supposed to be less than 1,000 ppm, but it always comes out way worse. And again, z squared minus y squared. This is a head-only system that we built, asymmetric, so it's curved at the back. So it's fundamentally a different design, or fundamentally, it's a somewhat different design from our conventional way of doing things. And again, we get this exactly the same field pattern in our magnetic field lines, in our magnetic field plots, z squared minus y squared. So that was frustrating, especially because these inhomogeneities, even after shimming, it's really difficult to deal with this. Like, this is really, you want to be much closer to this than to this. What we came up with as an explanation was basically, when you cut the holes to put the magnets inside, that hole has to be a little bit bigger than the magnet that you're pushing inside, just because of friction and things like that. So that magnet can, once it's in location, rotate a little bit. It's an in-plane rotation. And if you simulate that as a random rotation, you get field line, you get a little bit worse homogeneity, but you don't get these distinct patterns. But obviously the magnets themselves, when they're in place, they will feel some torque because of the nearby magnets and the main magnetic field. And that torque has this cosine, or sine 2 phi pattern on it, where phi is the azimuthal angle as you're going around in the circle, so the polar angle. And if you say, well, if there's a positive torque on it, well, it can rotate to the right. If there's a negative torque on it, it's going to rotate to the left, then it's right, then left. What you end up with as a field pattern is this. So this is 33,000 ppm if the magnets can rotate 1.5 degrees, which is not a lot. And if we put that against the magnet for which we simulated this, it's a very good agreement. So that really shows how important it is to build your system well, because a 1.5 degree rotation is really not a lot. What we now do actually is we compensate for it. So we say, hey, it's going to want to rotate. We're going to rotate it a little bit beforehand in the opposite direction, so that once it's in its proper location, it will be more or less correct. So that's what we did for the newest magnet that we built. And you see, instead of a z squared minus y squared dependence, you see a y squared minus z squared dependence. And that's because we overcorrected a little bit. But actually, in terms of ppm, it's the best magnet we've built. So yeah, it's hard to build these things well, really hard. So for shimming, I have to go through this very quick because otherwise I'll run out of time. But for the shimming, we use just a whole bunch of magnets that we defined a grid on which we could place them. And then basically we set an algorithm loose on it and said, hey, you can either place a magnet there, you can place no magnet there, or you can place a magnet but pointing in the wrong direction. Given the field map that we acquired with the robot, minimize the magnetic field distribution, minimize the magnetic field inhomogeneity by filling this grid. So that's what we did, and that worked quite well. So we were able to get down to 2,500 ppm. So it's still way worse than commercial systems, but this is something that you can start imaging in. This is not. I'll skip over the resonance for now, just because that's probably the most flexible part, and I think probably also where maybe is it fair to say that that's where you guys have the most expertise as well. So I'll jump on that one last. So we'll start off with the gradient coils. So the gradient coils, there's a couple of design considerations that you have to make, and they're all trade-offs. So you can't have perfect for all of them. So this is a balancing act that you'll have to do, also depending on the electronics that you have and the system size and things like that. So first and foremost is gradient linearity. So if your gradient is not perfectly linear, you're going to have distortions in your images. Commercial systems also have gradient nonlinearities. They just correct for them before they show you, but they definitely do have them. Gradient efficiency, which is how strong are your gradients per unit current that you're putting through. And high efficiency means less heating because of, again, I squared R. And as I mentioned in the question before, the gradients do start to contribute heat and temperature drift. So this is something to be careful with. And then gradient coil inductance. So inductance is a measure of how much magnetic field you're storing, which means that when you're slewing your gradients, changing your gradient strength, if you have a high inductance, it means that you can change those gradient strengths more slowly. The reason that it's a trade-off here, for instance, you can double the amount of wires that you're putting on your gradient cylinder, which is great because now you have double the gradient efficiency, but your inductance will be 4 times as high. So therefore it will take forever to slew your gradients. So when you're building these, work with the specifications of your gradient amplifier and kind of decide on what are the trade-offs you're able to make there. So the math for this is kind of a little bit horrible. So we made a gradient design tool for Holbach-based systems where you can basically just play around with which gradient you want and what the performance of that gradient system is to come up with wire patterns. So if you want to play around with that, there's a 3/4 working version on GitHub. And once I'm done with this meeting, I'll upload the working version because we've had some bugs on this. But yeah, let's just help you avoid some of the math. So we use this gradient design tool to actually make our gradient coils. The math was developed by Bart de Vos, one of the students here in the lab. And you'll notice that this, for the people with experience on high field systems, that this is your Golay type coil, which is what is your Y and your Z gradients on, your Y and your X gradients on high field systems. Yeah, we have that as well, but then the Y and the Z gradients for us are very different in design. And these two are much more efficient by about a factor of 2 than the X gradient coil. So typically this will be your limiting factor, both in terms of efficiency and in nonlinearity, because you see quite strong gradient nonlinearities here. To build them, get a 3D printer. Actually, for everything with low field, 3D printers are your friends because it just makes everything so much easier that you can build it in-house. We 3D print gradient formers, and then we use super glue and copper wire to basically construct the set itself. It's not that much fun to do this, but the result, it's quite easy to do. One of the things to be aware of, though, is that as with anything, with any conducting surface, your gradient will self-resonate, which means that those self-resonances will interact with your RF coils if you're not putting proper shielding in place. So make sure that you're putting a shield between your gradient coils and your RF coils, because otherwise it'll be a nightmare. So your gradient amplifier, basically is used to put current through your gradients, obviously. And your gradient coils are large inductors. So if you want to have a fast rise time on your gradients, you don't want to integrate your current over time, or you do, but you don't want to integrate a constant voltage over time to get your current. So typically gradient amplifiers are current controlled, which means that they'll have they'll overshoot your output voltage to lift the current up to its desired strength much more quickly. This is one of the power limiting things on your gradient coils. Typically the voltages aren't very high because your resistances aren't very high, but they are high when you're switching your gradients. A higher voltage will give a higher rise time. For us, the gradient system was by far the most noisy part of the system. So if we didn't properly take care of the noise, our noise went up about 400-fold when we switched on our gradient amplifier. It's also by far the largest power consumer in the system. So it's a huge noise source electronically. The gradients themselves on low field are essentially silent because your Lorentz forces are so small on the gradient coils because your field is lower, so much quieter. For the gradient amplifier, we just developed it ourselves because one of the things with low field is that there's not a lot of vendors who will supply stuff for low field to the gate. We hope not. It's a good question. Our magnet's been very stable over time. So we've had our magnet for about 3 years now, I think, 2 or 3 years.
Sorry, Tom. Can I read the question for the audience? Okay.
Oh, sure. Yeah, I can do that too if you want.
So there is a question on the chat.
Yep.
Do the gradient vibrations degrade the magnet positioning?
Yeah, and the answer is I don't think so, because the field homogeneity and the field strength has not changed over the 3 years that we've had the system. And that's the best answer I can give you because we've not actually looked at that ourselves. For the gradient amplifier, typically for high field systems, they're switch mode amplifiers. So they will have switching electronics inside of them, and switching electronics are noisy. And at high field, it's easier to filter out those noises because you're so far away from DC. Whereas for low fields, 2 megahertz, it becomes a little bit harder to filter these out. So a lot of commercial vendors will sell you gradient amplifiers, claim that they're low noise, but when you hook them up, they're terrible. So we ended up just developing our own little amplifier. It's much weaker than conventional systems because we want it to be battery operated potentially. Again, because eventually we plan on having one of these systems in Uganda where the power grid is just not very reliable. So we can operate these with batteries. We typically don't because it's easier not to have to charge them all the time. So this is a fully open source design. And all of the schematics as well as the design documentation and things like that can be found on our GitHub page. To deal with the noise, we had to add some extra filtering afterwards on the output, and we also improved our gradient shield. And to show the difference, it's left and right is brain images which were acquired essentially with the same sequence before and after we properly dealt with the noise from the gradient amplifier. So it's really shows how important it is. I think this image is actually filtered and this one's not. So we saw about a factor of 10 improvement in the SNR. Oh yeah, that's the unfiltered image first. So this is compared to this because this is also unfiltered. So it really shows the improvement there. Okay, then the final topic is the resonance part. So I just wanted to briefly mention RF in MRI, just the way it's done at high field. Again, I know you guys are experts in this area, so forgive me. But so RF coils, we call them coils, not antennas, because we're operating in the near field regime. The transmit field, on the transmit coils, we want that field to be very homogeneous to prevent any shading in our images because of imperfect excitation angles, as well as changes in image contrast. and you want them to be efficient, and efficient in two ways. You want a high magnetic field per unit current, just because then you can give shorter RF pulses to get the same excitation. But you also want your electric fields to be very, very low. So it's kind of a two-parter there. And then on the receive side, you don't really care about homogeneity. What you really want is to be as efficient as possible. And the way to get efficient at high field is to use coil arrays that can be placed as close to the body as possible. So at high field, this is an image acquired at 3 Tesla, which shows the magnetic field distribution, the B1 field, so the field produced by your antennas in the human torso. And what you see is that the homogeneity is not great. So the blue areas you're under tipping, red areas are probably over tipping. So you end up with this quite strong shading in your anatomy, which is purely due to your antennas. And it's got nothing to do with, I don't know, weird conditions inside of the human body. And that's because the wavelengths, the wavelengths that we're dealing with at 3 Tesla, so 3 Tesla is on 126 megahertz, I think, or 120 megahertz. The wavelengths are quite long in free space, but because the wavelengths scale with the epsilon, so the permittivity of the human body in the anatomy, it's actually quite short. And as that wavelength approaches the dimensions of the human body, you get these kind of standing wave-like effects. So at high field, it's very hard to get homogeneous RF. Tissue heating is a huge problem, and it gets worse the stronger your magnetic field gets. Very roughly speaking, your SAR, so the tissue heating, scales with the electric field squared, and the electric field itself scales with frequency. So you end up with, if you double the magnetic field strength, you get 4 times as much SAR. And then this is not per se a disadvantage, but it's just a general practical thing, which is that at high field, you're completely sample noise dominated. So when you put the antenna near the body, the electric field is going to interact with the conductivity inside the body. I'm pretty sure that should be a sigma. And that basically adds a giant resistor to your coil. So it doesn't really matter how well you build your coil, because the losses caused by the interaction of the coil with the antenna are going to dominate any losses that you're going to have inside of your coil. So at low field, this is not true because our wavelength is 150 meters. Tissue heating is not an issue because it scales with omega squared, and we're, let's say, 100 times lower in magnetic field strength. And coil loading is also really not a factor, or sample loading is not a factor at low field, again, because of that scaling with the electric field. So what does that mean? Well, it means that you're entirely coil noise dominated, which really is a kind of a different regime to operate in. It means that your coil arrays are less useful, because the reason that we use coil arrays, or one of the reasons that we use coil arrays, is to reduce the sample losses per coil, basically. It also means that our coil coupling is incredibly high, because 2 reasons. Typically, the Q of your coil will be higher, but also you have no signal attenuation inside of the body either. So if you have a coil at the top, a coil at the bottom with a lossy sample in between at high fields, the RF will be attenuated from one coil, will be attenuated by the time it gets to the next one. At low field, that doesn't happen. So these coils, they might as well be directly on top of each other. Your Q factors can be way higher, which is good for SNR, because your SNR scales with the square root of your quality factor, but it's terrible for your coil bandwidth. So the coil bandwidth will decrease with 1 over Q. So actually, to deal with this, we typically add a resistor to our coil to increase the bandwidth, knowing that that's going to reduce the SNR that we get. But if we don't do that, we just cannot acquire signal outside of our bandwidth. So just to show you, these are some S11 plots of a solenoid, like a decent solenoid, which is the orange one, and then the blue one is the standard one that we use for imaging. because we need to acquire signal from within that region marked by the black dotted lines, right? So if we look at the high Q coil, we're essentially not picking up anything by the time we get to our edges of a field of view. And you really see that coming back in images here. So these are phantom images that acquired on a ball, with the blue line being the frequency encoding direction and the orange line being the phase encoding direction for coils with 3 different quality factors. So the quality factor of 88, off the top of my head, it's, I think, a 23 kilohertz bandwidth on a 20 kilohertz imaging bandwidth. You see a little bit, or you see quite a bit of frequency dependence in the frequency encoding direction, whereas in the phase encoding direction along the orange line, the signal is completely flat, apart from the noise, obviously, but it's pretty much flat. And then as you increase the quality factor of the coil, you're narrowing the bandwidth that coil is sensitive over, and you end up with a huge decrease, like a lot of signal here in the middle. But towards the edges of your field of view, your SNR is actually lower than it is for your low Q coil. So that's why we use the resistor inside of the coil, because when we're imaging, we want to be able to see our entire anatomy and not just the central part of it. So that's annoying. And we're working on methods to try and improve this, but it's tricky. So finally, the RF amplifier is, again, this is something we developed ourselves because not a lot of companies will make RF amplifiers at 2 megahertz, especially not the kind of the strength that we need. So it's a 1 kilowatt RF amplifier, which is much lower than for standard MRI scanners. But you know, our RF coils are smaller. We don't have a body coil. We'll typically have a head-only coil or a local-ish transmit coil. And the losses in the RF chain themselves are lower because 2 reasons. We could put the RF amplifier directly behind the magnet, but also the wavelength effects are again less. So the power dissipation inside of the inside of the transmit chain is less. And it is a 1 kilowatt amplifier, but it's only on for less than 1% of the time. So it doesn't actually produce that much heat. The schematics are available. We've published them, but we're working on a simplification just because it's a little bit harder to build than we'd like. So yeah, this is something that we're working on improving, and once it's improved, we'll definitely share that again. And then finally, the spectrometer. So that's what you're actually going to run your MRI pulse sequences on. It generates the RF and the gradient waveforms and digitizes the signals coming in and things like that. At the moment, this is by far the most expensive component of the system. So this is made by a German company called Magritech. It's about 25,000 euros, which is 3 times more than the rest of the system combined. So we are planning on replacing this eventually with an open source alternative, but it's taken a lot of work. So this is what the system looks like. We have the whole system placed inside of a Faraday cage. The magnet, the gradient shield, the RF coil, and then the amplifier is directly behind it. When we're imaging, though, we do have an issue here that the body acts really as a very good noise antenna. So if the body is sticking out of the Faraday cage, the noise will come in and completely destroy your image. So it's about 50 to 100 times more noise. Depends a lot on your coil design. So we found that if we use a conductive cloth that we place over the patient and make sure that cloth is connected to the Faraday shield, then we virtually eliminate all that noise that's coupling in. On the reconstruction side, people always say, oh, use machine learning. We don't have a lot of expertise in machine learning, at least not in our low field group. So for now, our image reconstruction is just literally a Fourier transform of the data as it comes in. So there's nothing fancy going on there yet. But these are the images that we've been able to get. So these are some in vivo knee images that we acquired in under 10 minutes, which is surprisingly good, to be honest. And then whole brain images, which start to show some distortions. But again, this is something we're not correcting for gradient nonlinearity. or B0 distortions at the moment. So I think once you do that, then the anatomy will be somewhat better represented. But SNR, it's not bad. Contrast is very low, but that's yeah, T1s get very close together at low field, as you can see on this, because we've been able to do some relaxation time mapping, that there's not actually that much difference in the T1 times between gray and white matter, for instance. It's much less than it is at high field. So it's harder to generate that contrast. So those are some of the imaging experiments. And then what does the future hold for us? Well, we're working on, we want to see a broader adoption of open source technology in MRI, because I think we're in a position now where the technology is becoming so available to people that we can start doing this. So I've been working together with Lucas Winter from the Open Source Imaging Initiative to basically generate or to create a low field system where everything is available and where we will help as much as we can for people to get the system up and running. So it's based on a lot of the learning from the system that we had before. So it's again, it's a 50 centimeter long Hallback array. It's a little bit heavier because we made the bore 30 centimeters instead of 25 centimeters. But we'll provide all the drawings, the 3D print files for the gradient coils, for the RF coils, for the electronics. And we're looking at options where we would, for instance, order a batch of the electronics or order a batch of the materials needed to construct the magnet to help other groups set up their own system. We're targeting a cost of somewhere between 10 and 20,000 euros. These are material costs. Like, we're not interested in making a profit on that. But we feel that this is something that's achievable at the moment without the economies of scale and anything like that. So yeah, we've had about 20 groups sign up for it so far. I have to see how many actually will build the system, but yeah, I think it'd be cool the more that we can kind of work together on this stuff, because there is so much to figure out, the better. That's not supposed to be there yet. So what are the main takeaways of the talk? On the magnet side, you can be flexible with the design. I think a lot of the MGH stuff is really cool, whether using these single-sided or somewhat single-sided magnets. So think outside the box, but be aware that construction is much more difficult than design. It takes a day to design a magnet. It takes months to build a proper magnet. For the gradients, it's kind of a no noise / noise. They're silent. You can kind of hear a low hum when you're imaging, but just be very aware of electronic noise. This really is by far the biggest noise source inside of your system. And the RF coils, forget everything you've learned at high field. And there is definitely such a thing as too good, just because you'll start noticing it in your bandwidth. So thanks for paying attention. I think I was even on time, and feel free to ask any questions that you guys like. I know that was very, very quick, but yeah.
Yeah, very nice. Thank you very much for your interesting talk. So dear colleagues, do you have any questions to Thomas? Please raise your hand or some questions in the chat. So maybe I have a question. Mm-hmm. So Tom, what else you can DIY without, like, not an MRI, but for medicine? What else do you do? Here in the hospital? Yep. We only work with MRIs. We're part of the MRI group. From the open source side of things, there's several other groups which are looking at open sourcing ultrasound systems to make them more available. CT, I think, is just difficult because of the radiation issues. Yeah, but we mainly focus on MRI. Okay, and is there any possibilities to send to you some student or PhD student to study such nice engineering things as you're doing?
I don't want to speak for my supervisor because but I don't see why not. I think we worked nicely together with Elena before, right?
Right.
So yeah,
We need to discuss it with Andrew, Dima.
Yeah, I don't want to speak for Andrew. Yes, but I know we'd be open to it. Yeah.
Yeah, like, sorry, I'm not from the MRI community. I'm not very like well known about that.
It's okay. That's okay.
How many people actually was involved in the project? Because it seems that you built a lot of things, not only the magnets and coils, but also some preamps.
So a lot of the electronics were done by a guy called Danny de Gans in Delft, because we don't have that much of an electronics background. Like we can do coils, we can do very like typical MR things, but when it comes down to building amplifiers, we don't have that knowledge. So for that, we worked with Danny de Gans in Demo in Delft University. Then we had Bart, who did the math behind the gradient coils. And then Wouter Theeuwissen, I think you've met Wouter while you were here.
Yeah.
And myself really did a lot of the construction side of the system. And then, yeah, a lot of it, a lot of it was just me doing things.
So
you build it over time, so it doesn't feel that much. But yeah, looking back now and making that list, it was a lot of work.
Yeah, okay, thanks. We have a question from the Georgi Salamacha.
Yeah, Thomas, thank you very much for the talk. So I have a general question. What do you think, what will be the best methods to reduce the time of scanning in your system or in similar systems? So what is a general guideline how we can do this? So it's because it's, as I understand, it's not possible to use like parallel receive methods here. So what we can do to reduce the time of scan or improve the quality with the same time?
Yeah, so it's a really good question, because I don't have the answer for you. I think quality-wise, we're looking at using some of the methods. So I don't know how familiar you are with high field systems, but on high field systems, you can use something called preamplifier decoupling to reduce the coupling between your coil arrays. So what you do is you have a low input impedance preamplifier. You have a quarter wavelength impedance transformer, which transforms it to a high impedance on your coil. And you use that high impedance on your coil as a lossless way of destroying the quality factor of your coil.
Yes.
So you destroy the quality factor, but you don't add losses. So you should keep the same SNR. So we're working on trying to get that to work on low field, because in principle, that should get rid of this frequency weighting because you've destroyed your Q factor without adding losses. So in that way, we should be able to get the SNR that we can get with these high quality factor coils at without the frequency weighting. So with the same frequency weighting as this. So it's something we're looking at, but you can't buy a lot of these amplifiers. Excuse me, you can't buy a lot of these amplifiers for low field. So that's where we've been like focusing on the development there. On the other side, on the acquisition side, we use Fourier transforms to do the reconstruction. If you got the raw data from a Philips system or a Siemens system and you did a Fourier transform, the image would not look as nice as what's shown on the screen. So there's a lot of data processing that's happening there, but that's all vendor specific knowledge. They will not share that information with you. So for us, on the data processing side, I think there's a lot to improve on. And then obviously you can't mention low field without mentioning machine learning on the reconstruction side. I think there's probably quite a lot of interesting things that can be done there. But even without machine learning, doing proper data processing will probably help quite a bit on that. And then you should be able to reduce your scan time, or at least improve the SNR. And then you can use sort of conventional ways of reducing your scan time, like half Fourier methods and things like that, which are non-parallel imaging ways of reducing your scan time. So there is room, but I think mainly on the SNR side rather than reducing scan time side.
Yeah, okay. So yeah, maybe a small stupid question. So generally you need something with a very high, very low noise figure and with very high input impedance to reduce the quality factor. So but did you try just use the operational amplifiers?
Yeah. Yeah, we have that now. We finally got the parts 10 days ago. So we've just started doing some testing, and it looks promising. The Q factor definitely broadens. It's just the SNR is not quite as high as with our standard systems yet. So it's
I think it should be. Yeah, it seems that it should be some specific type of this amplifier. Wow, cool! It's like a new. So and yeah, it's like a kind of connected question that maybe so your frequency is quite low in terms of RF, but you already use like your RF power amplifier, and your RF power amplifier is just having the 50 ohm input, and then you match the coil to the 50 ohm. Is it possible to use something like transmit preamplifier decoupling, or just a transmit just RF transmit current source? Because I know that there was several work from NIH in the zeros that transmit coils also could be decoupled, but here it shouldn't be like in terms of decoupling, but in terms of the quality factor. Did you try to do something like this?
We haven't yet, but we have a student starting in April who will probably look at that. So is that the work on the non-resonant coils? Is that what you're referring to?
No, it's not non-resonant coil. It's just the coils with the current sources, with RF current sources. So you have you just drive your coil with a very high impedance. So yeah, I can share some links.
Oh, that'd be great. Yeah.
So because so I think that generally it's possible, not just using like 50 ohm source, but maybe something 2 kilo ohms or something like this, and it actually should at least somehow solve the problem of quality factor in transmit.
I think so. Yeah, I think so, because that's kind of a thing that I brushed over in this talk, is that this is talking about the receive side, but also if you put a sample inside of your coil, depending on exactly on your coil loading, the frequency is going to shift a little bit. So if that happens and you're transmitting high power into a coil that's no longer 50 ohms, then that's also going to be a problem. So I've spoken about this high Q being an issue on the receive side, but like you say, it's on the transmit side, it could also be a problem. It's just we've not particularly looked at that yet. So it's cool that there's other groups who have thought about that, or
similar so it's just so I have like overlapping of two talks, because like 1 year ago we have to talk from Australia about this Linac MRI system, and they also use like a very low field scanner, and they describe this problem generally in transmit. And when I saw this your quality factor problem, I also remember this. So yeah, thank you very much. It's very impressive,
thanks for the suggestion.
And I hope that somehow we will also join this.
Yeah, very cool.
Yeah, thank you very much. Do you guys have any other questions, Tom? So if not, I'd like.
Okay, Tom, thank you for agreeing to give this fascinating presentation. I think it was very useful for our group, and so I hope that if we will have any further questions when we will start to work on the project, we can ask you.
Absolutely, yeah, absolutely.
Thank you very much. Thank you.
All right. Stop sharing my screen. There we go.
Thank you very much, and see everybody probably see everybody next Monday again. Again,
All right.
Goodbye.
Thanks, guys. Bye.
Goodbye.